What's up guys, Mixmaster Ameron here. Today we're going to be doing a video on projectiles. So first things first, I'm going to be doing a definition on just a general projectile, and so let's get into that. Projectiles are objects which once projected into the air are not self-propelled, or they don't have wings or anything to hold them up. So basically a projectile, once it's shot, is going to be eventually pulled down by gravity hitting the ground. So we're going to start off with a Type 1 projectile. There's three different types of projectiles, and we're going to go through all three of them, and the differences, similarities, and yeah, so let's get right into that. So our first type of projectile here is just one that is shot at a horizontal, meaning it can't be shot at an angle of 45 degrees, 50 degrees, so it's just shot completely flat, can be off a cliff, up towards a hill, on a flat field. The displacement does not have to be zero. It just has to be shot flat. That's basically the only rule with it. So in our Type 1 projectile picture, here we got a picture of a potato cannon, and the dotted line, it shows the arc of the potato leaving the gun. So basically what happens is it's just shot completely flat, and it just, like gravity, just pulls it down to the ground and it stops. An interesting note with projectiles, type 1, 2, and 3, is in the x-axis, our velocity initial and velocity final are always going to be the same in regards to completely neglecting any air resistance. So the velocity when our potato leaves the potato cannon and right before it hits the ground in the x-axis is going to be exactly the same, because the acceleration in the x-axis is 0, meaning it does not speed up after being shot, therefore it is a projectile, and it does not slow down because we neglect air resistance. Starting into our calculations for Type 1 projectiles, at the top of the page here we got calculations 1, just representing what calculations we're doing. Top left corner we got our knowns and unknowns in the x and y axis. We got velocity final, velocity initial, distance or displacement in some cases, acceleration, and time. Then you can see below there you got your x-axis calculations, and you'll notice there's not actually that many equations or calculations used here. That's simply due to measurement during the experiment. So we used a tape measure to measure our distance for this certain case. So we, right off the bat, before we did any math, we knew that the distance shot with our Type 1 horizontal shot was 60 meters in the x-axis, and we knew the stand that we sat it on was 0.6 meters tall. So that explains the red underlines under velocity initial, distance, acceleration, and time on the y side, as well as underlines under distance, acceleration, and time on the x side, because those just represent what we knew before we actually did any math. So those are just basic things that we already know without doing any math. So we just had to find our velocity final, or our velocity initial in this case, for our x-axis, because they're going to be the same, and in our y-axis we simply had to find velocity final. So to do that, we knew our velocity initial was 0, so that's why there's a big 0 with a cross through it. So that part doesn't matter, we forget it. And then we just add our acceleration and times our time, which equals our velocity final. In this case, our velocity final turns out to be negative 12.74 meters per second. You're probably wondering why it's negative. Well, this is in the y-axis, so our velocity final is going to be negative because it is falling in the down direction. So it's going at a positive velocity in the negative direction, making the velocity negative. To solve for those different unknowns, so it's going to be a lot more time consuming. The only reason that we have these is because we were there and we used a tape measure, for example, to get our distances, which made things a lot faster, made calculations a lot shorter. So just keep that in mind. It's never going to be this easy. You're always going to be given less variables than this on a test quiz. We got 46.15 meters per second equals our initial velocity in the x-axis. We got the same equation that we used before for our type 1 projectile. D equals VIT plus 1 half AT squared. In this case, 110 equals VI times 6. And then, again, we completely forget about that second part of the equation because the acceleration in the x-axis is 0, canceling that all out. We then continue to divide by 6, getting 110 over 6 equals VI, which is 47.73 meters per second, which equals our velocity initial in the x-axis. Our y-axis, I just worked my way through the equation. D equals VIT plus 1 half AT squared. D in this place is displacement, and it's 0 because the launching surface and the landing surface have the same elevation. So this makes things really easy. We do the exact same things we did for the x-axis, except for in this case we actually have an acceleration, which is negative 9.81. And if you follow the equation here, we get to the point where 176.4 equals VI times 6. We simply divide the 6 over, and we get 29.4 meters per second equals our velocity initial in the y-axis. Bottom of the page here, we've got a right triangle, and at the hypotenuse you can see 56.06. I know what you're saying, I don't know where the heck this came from. So all we did was we made a vector diagram, and we went head to tail with our different velocities. So the 47.73 connects to the 29.4 meters per second, and we just make a triangle out of that for our velocity resultant. So that's the muzzle velocity that the potato leaves the muzzle or the barrel of the cannon. So to find that, we did some simple Pythagorean theorem, and we went 47.73 squared plus 29.4 squared equals 56.06. Then again, we square rooted the answer from the squared A and B, which equaled 56.06. And the angle of 32 degrees, which we already knew from launching, we simply took tan inverse equals opposite over adjacent. The reason I threw this in here was just to show how you would find it if you didn't know the angle already. Like I said in a previous problem, that sometimes on the test you're not going to be given these variables because you weren't there. So oftentimes you're going to have to find that angle. To do that, we took tan inverse opposite over adjacent, which was our 29.4 over 47.73, which equaled 32 degrees. Simple definition for our type 2 projectile would be launching an object at, let's say, a 45-degree angle, any angle above horizontal, meaning that it's going to add lift to the object being launched. In addition to that, the surface that you're launching at has to be the same elevation as the surface that the ball, potato, whatever you're launching is going to land at. Therefore, the displacement in the y is going to be 0. So it must launch at some kind of angle, and it must land at the same elevation that it was launched. Zero displacement means that our field is flat, meaning when we shoot our object at, let's say, 45 degrees, it launches up to the top of an apex, and it stops completely in the y-axis. This is due to the deceleration of gravity. When it reaches that apex, at the top of its tallest distance, it's going to have to go back down that same distance, meaning that gravity is going to continue to accelerate it down, and when it reaches the point that you record your velocity initial, your velocity final at that same height is going to be exactly the same, but opposite, due to the falling distance and the pull of gravity down on the object. Meaning that it will have the same amount of time to accelerate down as it did to decelerate to the top. However, by definition, a Type 3 projectile has a non-zero displacement, meaning our launch elevation is different from that of our landing elevation. So we could be launching off a cliff, we could be launching up a mountain. As long as we're launching at an angle and we're landing at a different elevation than we started at, we're going to have a Type 3 projectile. Unequal falling time is causing our final velocity in the y-axis to be far greater than our velocity initial in the y-axis because we simply had more time to fall down than we had time to get to the top of the apex. So the distance from the top of the apex is much farther to the landing destination than it is to the starting destination if we're launching off a cliff, causing that velocity final to be far greater because it accelerates for a longer period of time. To find our hypotenuse for a right triangle, kind of in the middle of the page on our type 3 calculations, you'll see a 43.15. That is our muzzle velocity from the angle that we shot at. I actually got that number from our horizontal launch on our type 1 projectile. So from that number, I just did some basic trig and got my x initial velocity and my y initial velocity, just shown at the bottom in brown and red.
I have my velocities found. I moved into finding my distance in the x-axis and my final velocity for my y-axis. I didn't have to find my final velocity for my x-axis because I knew that it'd be exactly the same as my initial velocity. So for my final velocity, I used the equation VI plus AT, which equals my velocity final, which was negative 38.1 meters per second. I know that it's negative because it's falling downward. It is going at a positive velocity in the negative direction, making the velocity negative. For our distance, we got 213.5 meters. I used the equation D equals VIT plus 1/2 AT squared. That was pretty straightforward. I plugged in my initial velocity, my time, and then the rest of the equation I completely just forgot about because the acceleration is 0 in the x-axis for any projectile.
Landing in the